That works well. Now for something more exciting. In fact, I don't think I've done this before, so it's going to be exciting for me too. What sort of stuff does Mac OS X run when you run man? Better find out. Ah! Grotty? What's Grotty? Grotty, graph driver for typewriter-like devices. Oh, okay, cool. Which I have, yes. So there you go, exciting. I can discover things I didn't know before. Wonder if there's a trotting, yes. So, of course, just to throw it in here right now. Okay, let's do this really. So printf. This is just going to seed your mind so you have more, something a bit more concrete to chew on. So, okay, I can do things that are more interesting. I'm now printing out nanosecond timestamps for those events. And this is why DTrace becomes interesting, because you have high resolution time, which means you can identify latency and arbitrary points. I just happen to pick this system call. I can DTrace anything. So back to the presentation. You might have seen this before. I've used this diagram in a bunch of places. How did you analyze these before? It varies on your operating system. So dynamic languages like Java, JavaScript, Perl, Python, you use whatever debugger comes with it, or you edit the code and put a bunch of printf statements in it. User executables, user bin star, things that are compiled. You might point truss, strace, although that's actually giving you the syscall interface. On Solaris, you could look at the user executable calls if you used AppTrace, or you can run through a debugger. Libraries, same deal, AppTrace, debuggers. LD preload, put your own stuff in there, just shim all the calls. Syscall interface, of course, is fairly easy to analyze, because there's a bunch of things that do that, like truss and strace. Diving into the kernel, that varies. There was ways to do this before in Solaris. Anyone know? Oh, MDB lets you step through it live. But if I just want to find out what's happening and who's consuming CPU time and find out how the kernel is behaving. Lockstat lets you do it. Lockstat minus cap I, and you can profile it anyway. These days, it's another way of saying DTrace. And Prex and TNF were there as well for Solaris. I don't have this list for Linux, but you can picture in your mind that, at least on Solaris, it's a bunch of different tools to get observability across all these layers. And I imagine it's the same for other operating systems as well. DTrace makes it easy because you learn one tool, and I can see anything, except for the hardware. DTrace can probe anything that happens on the CPU. So I can infer things about the hardware because I can DTrace the device drivers and see what they're up to. Sure. So DTrace is like, if you're a Solaris person, DTrace is like joining Truss, AppTrace, Prex, Lockstat, and MDB. So you can access kernel virtual memory, and you can also access process virtual memory as well. As an example, just picture strace if you're not a truss person. Truss is a command that shows you all the syscalls. Truss date, and I can see execve, resolve path. It's going through the system calls as it runs date. Truss can only examine one process at a time. The output is limited to the provided options, so I don't have control over that. Truss gives me what it wants. There are some switches. Truss also slows down the target a lot. Using DTrace, so I choose the output that I want. I get to watch every process. I don't have to point at a particular process ID or command name, and it has minimum performance cost. Minimum performance cost. How that works on Truss used a procfs interface, and I assume strace does the same thing. It uses a procfs interface to get the process to break whenever it enters or exits a system call, and context switches off so that trust can context switch on, do some procfs things, find out what that process was doing, and get debug information that way. Since every time a system call is firing, you're breaking and context switching and breaking and context switching, it can slow down the target a lot. If you're doing 1,000 system calls a second, you might be doing 2,000 context switches a second just to debug it. With DTrace, DTrace lives in the kernel, instruments in the kernel. If I'm running a bunch of system calls, it will buffer the trace data and not context switch on and off for every event. So DTrace, the user land program, which I'm running at the command line, it will step onto the CPU at a leisurely pace, once a second by default, and read that buffer. So you go from interrupting the application in a very violent way, like what Trust does, to letting it run at its own speed, almost, buffer that debug information, and then you've got control over how quickly you read that debug information. Once a second means you may only be context switching a few times. That's really good, as opposed to doing, say, 10,000 system calls a second and 20,000 context switches. What's DTrace for? Troubleshooting software bugs, proving what the problem is and isn't, measuring the magnitude of problems is important. Detailed observability, observing devices such as disk or network activity, applications, whether they're from Sun, Apple, third party, in-house, capturing profile data for performance analysis, in particular latency. If you're a Solaris person, DTrace isn't a replacement for KStat, the kernel statistics framework, or SNMP. Those things still have value. So KStat provides inexpensive long-term monitoring. I believe Linux does that through various things in /proc. SNMP is for network monitoring, and again, that's long-term monitoring. DTrace is designed for the short-term, from broad to deep analysis. You can use it for long-term monitoring, and we do at Fishworks, but you use KStat if it's there, or you use DTrace if you need to do more. It isn't sentient, it does need to borrow your brain to do the thinking, and we like to spell it with a capital DT. It's for application developers, because you can fetch in-flight profiling data without restarting the apps, even on customer production servers. Detailed visibility of the functions you've written and the rest of the software stack, which is really important. And you can also add static probes as a stable debug interface. So for application developers, I've worked with a lot of application developers who are excellent at debugging their layer of the software stack. There may be low-hanging fruit in other layers of the software stack, the way they're interfacing to libraries, the way they're interfacing to the operating system, but that's not their field of expertise. They're Java developers, they're excellent at looking at Java, but it's something in libc is actually holding them back, which comes from a true story. So DTrace gives you the ability to look across everything and get that low-hanging fruit from other areas. Application support, comprehensive insight into application behavior, analyze faults and root cause performance issues, prove where the issues are and measure their magnitude, which is especially helpful for priorities. System administrators, troubleshoot, analyze, investigate whenever before, and see more of your system. Fills in observability gaps. And I wrote the DTrace toolkit in particular to help system administrators to get some value from DTrace quickly without needing to learn DTrace to start with. Although we encourage you to learn DTrace. You can learn DTrace from the simplest scripts in the DTrace toolkit and see how they work. Database administrators, because I can see performance across all components. Security administrators can be useful for short-term auditing. Kernel engineers, DTrace is extremely useful for because we get to see kernel trace data from every function, functions that we write. The function arguments are auto-casted, so I can walk struct members in a very convenient way. I can get nanosecond timestamps out so that I can find where that latency is really well. I can troubleshoot device drivers, including during boot. And I can add my own statically defined trace points for debugging. So extremely useful for kernel engineers. You can use it either by running pre-written scripts, one-liners. There's some on the Solaris internals website, on the opensolaris.org website. You can write your own one-liners and scripts.